let's go ahead and get started. The last time we were talking about heat intensity in watts per square centimeter going from 10 to the third to 10 to the sixth. Below 10 to the third, you don't have enough heat going into the material rapidly enough to bring the surface up to melting. Above 10 to the sixth, at 10 to the seventh, you're vaporizing things and drilling holes rather than leaving molten metal behind and producing a weld. So today I want to go into flames, and you're going to see right here, this is an oxyacetylene flame, this is an air methane flame, and there's about an order of magnitude difference. This is an oxypropane flame, and there's about a threefold difference in the heat intensity for propane versus acetylene. There's also about a tenfold difference between oxygen and a hydrocarbon flame, air hydrocarbon flame, like a Bunsen burner. So we want to talk about why that's so. If you go through the theory of combustion, of surface heating by combustion, there's something called a combustion intensity. Now, if you go to the literature, you have to be careful, because a lot of people, when they're talking about combustion, they're talking about heating up a great big boiler, like at some electrical utility plant or something, and they're trying to heat up water to make steam to make electricity. And their combustion intensity is in watts per cubic centimeter, because they want to talk about the burning within the volume of the boiler. Okay, we're interested in a surface heating, so we're interested in combustion intensity in watts per square centimeter, which is the same units as what I just showed you at 10 to the third, 10 to the sixth. That's good for welding. So the combustion intensity is equal to the heating value of the gas, which has units of joules per cubic meter of gas that you're burning. So that's joules per unit volume, times the gas velocity in meters per second. Well, it turns out the heating value of the gas has got to be proportional to the temperature at which the gas burns. That's not too hard to guess. I mean, if the gas burns at a higher temperature, then obviously it's going to be able to supply more heat. There's a bigger delta T. And the gas velocity in meters per second is directly proportional to the temperature, because the gas velocity is basically just created by the PDV, the increase in volume. As the gas heats up and burns, it expands, and that's what causes the gas to make a noise as it's expanding. If I take this, you can hear the velocity. You can see it shooting in one direction. Okay, and we also know that even though this is high intensity, if there's not a very long interaction time, you can actually pass your finger through there and not burn your finger, as long as you don't slow down. You would burn your finger, which actually leads me to the review over here. I forgot. The heat intensity, we talked last time, determines the heat efficiency, heat effect zone size, travel speed, interaction time, automation, need for automation, equipment costs, depth to width ratio, and production volume requirements. All those things come out of the heat intensity. If anyone ever comes along with a new welding and joining process, then you can go to the same graph and you can determine how useful it is. A number of years ago, about 10 years ago, when peace was breaking out, the Defense Department had spent $500 million developing particle beam weapons. And these were basically beams of electrons that they were supposed to be able to shoot through the air at an incoming missile. So if you were a ship that was being fired on by some missiles from 30 miles away or something, which would be typical engagement length in a typical naval battle, if we had such things anymore. Anybody know why we don't have naval battles anymore? Aside from the fact we don't have big shooting wars. I mean, the biggest naval battle that I know of in the last 25 years was basically when the Arabs and the Israelis, they had some PT boats go out there, little things go out and fire on some others. So it's kind of like something not much bigger than a big, good-sized sailboat going out and fighting with each other. It turns out one of the reasons is, the U.S. Navy today has more capital ships than all the rest of all the navies in the world combined. Now they only have about 300 or 400 ships. And back in the mid-'80s, during the Reagan defense buildup, they were shooting for a 600-ship Navy. Now they're down to about 300 ships or something like that. But that still is more capital ships than all the rest of the world combined. So there's not a lot of other navies that want to go against the U.S. Navy. It's not a high percentage risk. might be a lot of terrorists who want to go against it, but then their risk, they have a different risk formula. In any case, so all these things come out of it, and when the Defense Department was looking at what do we do with these particle beam weapons, we spent half $500 million on because one thing, they didn't really work. They were supposed to be able to shoot down an incoming missile by shooting an electron beam through the air for 30 miles, and it turns out they were really only good for about 30 inches. Small problem, because the beam had some instabilities. They called it, one of them was a hose instability. If you take a garden hose and you just kind of turn it on with high pressure water out, it just kind of whips around like this, you know, in a random pattern. Well, the beam kind of whipped around in a random pattern. So if you had someone shooting a missile at you, you had to have a very cooperative enemy who fired your missile into your beam, okay? Because your beam couldn't hit what it was aiming at. Anyway, so they were looking for something to do with these things, and they had a 2 or 3 day workshop, and they asked me, they thought, well, we'll weld submarines together, and I said, okay. I came down, and I gave a presentation, and I basically gave the same presentation I gave you at the last class on heat intensity, and said, if you have a heat source, this is where you figure out how to use it. Now, it turns out these particle beam weapons actually had power densities, capabilities of 10 to the 7th and 10 to the 8th. And these people thought, this is fantastic. We can use this for welding. I said, no, you can't. If you want to drill, you can. They also had fantastic power capabilities. They could produce megawatts of power. And they thought that would be useful. Well, it turns out a typical welding operation, you're just trying to weld a seam of something. You're not trying to melt the whole thing. You just want to weld the joint. And that's typically not much more than 20 to 100 kilowatts. And these people could produce multi-megawatts. I said, well, maybe if you want to melt a submarine, you know, but you're not going to weld a submarine. The other problem with it is there were 1,000,000 volt beams, and they put out hard x-rays that required 3 meters of concrete to shield against. And so I said, I doubt they're going to take the 5,000 people in the shipyard and have them all go on a lunch break while you decide you want to start to weld. Okay, because you can't just kind of build 3-meter walls around everything you want to do. We did find an application for it, but it wasn't welding. In any case, last time I didn't really talk much about interaction time. I dropped the dollar bill and we talked about human interaction time. But you can think of the interaction time in terms of a fusion weld pool. You're going along some seam, and you got solidified metal behind you. The weld pool has some length L, and you're traveling at some velocity V. That way. And the formula is the length is equal to the velocity times time. The interaction time is just going to be the length of that weld pool divided by the velocity. As you go to higher power densities, the velocity is going to increase. The length will also increase, but not by a lot. The length of the weld pool might go from a centimeter in size to 5 centimeters in length, or some weld pools might be 10 centimeters in length, but it doesn't change by more than an order of magnitude, whereas this velocity can change by several orders of magnitude, and therefore your interaction time goes from a few seconds down to, in some cases, in electron beam and laser welding, milliseconds. And that's why you have to go to automation and things like that. So I just wanted to cover interaction time. But going back to surface heating by flames, what we find is the combustion intensity of a flame is going to be proportional to the temperature squared, because of the heating value of the gas and the gas velocity are both proportional to temperature. And so it should go as T squared. So the higher the temperature of the flame, the better off I am. We also find, and we'll discuss this in a little more detail in a little bit, the theoretical heat flux is 10 to 50 times greater than what we measure experimentally. Now, we actually said that the other day when I was talking about heating efficiency. And I said that the heating efficiency down at 1,000 watts per square centimeter is only about 2 to 10% efficient. Well, that comes from this factor of 10 to 50. If you're 10% efficient, then you're actually transmitting 10 times as much heat flux to the surface as actually is going into melting and going into the weld pool. If you're 2% efficiency, there's the factor of 50. And so we'll get to, I'll explain why we have that low efficiency in a second. Turns out that one summary of since the temperature, it goes as the temperature squared, we're interested in the temperature of the flames, and it turns out the temperature of the flame is first dependent on the enthalpy of reaction of whatever this chemical reaction is that's going on in flames. Now, we typically are burning hydrocarbons, and I'll ask the typical trick question, and you should know that when they ask a trick question, the answer is always the counterintuitive one, right? So which burns hotter, carbon or hydrogen in a hydrocarbon? I mean, carbon burns to CO2 or CO, and hydrogen burns to H2O. What do you think burns hotter, hydrogen or carbon? Someone guess. You got a 50-50 chance of being right. You got a 50-50 chance of being wrong. Carbon. Hey, that's counterintuitive, right? Because you were about to say hydrogen, right? You wanted to say hydrogen. And most people want to say hydrogen. It turns out carbon, if you look at the enthalpy of the reaction, actually has a higher enthalpy than hydrogen. If you look at 1 mole of carbon burning with 1 mole of oxygen, whether it burns to CO2 or CO, it doesn't matter, has a higher enthalpy of reaction by about 10% than burning a mole of hydrogen. But we think of hydrogen as burning hotter because actually it tends to burn faster. Before I put this up, why would hydrogen burn faster than carbon? What actually burns? What phase, gas, liquid, or solid, actually burns? The gas burns. Solids don't burn. Liquids don't burn. It's the vapor above the solid or the vapor above the liquid that actually burns. If you look at a candle, the candle, you look at where the flame is on the candle, it's levitated above the liquid pool of the candle. And that's because there's vapors coming out of the liquid fuel, or the liquid pool, and that those vapors, as they rise and mix with the air, it's the molecules of oxygen and the molecules of hydrocarbon in the vapor that are interacting. If you actually went through a kinetic theory of gases and said, how fast could I have burning if it was on the surface of a condensed phase, a liquid or a solid? Even though the Langmuir is 10 to the minus 8 atmosphere seconds, it turns out you get very little burning if you only have a surface of molecules to burn, and the oxygen has to reach that surface. Because you have to have the products of combustion, the other gases go the other way, and that slows everything down. And the only way you can get very rapid burning is if you have gases mixed together. And so hydrogen burns much faster because it starts out as a gas. If I had a carbon vapor, that carbon vapor, if I ignited it, would burn faster than hydrogen because it has more enthalpy of reaction and stuff, but and hotter. But we never see a carbon vapor. We always see essentially hydrocarbon vapors in a log in a fireplace and stuff. And actually, coal burns slowly because there is surface heating of coal, and the CO comes off, and then the CO burns as a gas. So it's actually a combination in coal. But anyway, combustion is a very, very complex field. If I plot the carbon to hydrogen ratio versus the adiabatic flame temperature of a oxygen burning, of hydrocarbon burning in oxygen, it turns out the adiabatic flame temperature of hydrogen, according to one calculation, is just below 2800 centigrade. And so that would be on the zero of this carbon-hydrogen plot. Acetylene, which has 1 hydrogen, 1 carbon, is the most carbon-rich hydrocarbon, and it has a flame temperature of about 3100, about 10% higher. And if I have methylacetylene, which is C3, I'll show you the formula for that. That's 0.75, it's here, and if I look at propane, it's down here at 0.375, or no, 311 is 0.33. And if I'd have methane down here at 1/4, methane would be right here if I actually had that on my graph. But you find kind of a linear relationship here. It's basically the enthalpy of burning carbon and the enthalpy of burning hydrogen. Hydrocarbons actually are a mixture of the two. And so that tells me the heating value of the gas or the enthalpy of the reaction. In addition, I have to worry about the stoichiometry of the oxygen-fuel ratio. If I look, this comes out of the welding handbook, at the oxygen to fuel gas ratio as a function of the fuel in the mixture. So we're looking at 100% fuel, 0% fuel. Well, obviously there's a 0 point down here, because if it's all oxygen and no fuel, then you don't get much heat, much temperature rise. And if you look over here, at 100%, you don't have any oxygen, so the thing's not going to burn. So there's got to be some peak in the middle. This is actually the normal combustion velocity. This is primary combustion intensity in BTUs per square foot, which is only the welding journal would use English units like that. This is secondary combustion velocity. But in any case, the combustion velocities are going to peak somewhere. The X value is the stoichiometric mixture, and the circle is the neutral mixture, where there is no oxygen left over. It turns out because of the what do you call it? The equilibrium constant for these reactions. You always have a little. If you mix things perfectly stoichiometric, so you have 1 mole of a hydrocarbon with the right number of moles of oxygen to get what the equation says is perfect mixing, you never get quite that complete combustion at the stoichiometric mixture, because the equilibrium constant is something like, well, if I did it for acetylene, some number of moles of oxygen goes to CO, I'll just call it CO2. It'll be 2 of those plus 2 H2O, or 1 H2O. So that's going to be, what, 3/2 oxygen? So if I had 1 mole of acetylene and 3/2 moles of oxygen, I'd end up with this, but the equilibrium constant says that that would be equal to P squared of CO2, the pressure of CO2, times the pressure of water vapor, divided by the pressure of acetylene and the pressure of oxygen to the 3/2. So if you look at the equilibrium constant for this, the reaction never goes to 100% to completion. You can't drive the bottom to 0, because the equilibrium constant is not infinity. So the equilibrium constant says you'll always have some unburned acetylene and oxygen, because the equilibrium constant is finite. That means that you don't get your most complete burning at the stoichiometric ratio. You get it somewhere on the fuel-rich side of that, where you're driving as much oxygen. You're driving the oxygen down as low as possible, and the neutral point's actually over here. But in any case, so you have these peaks, and you get your maximum burning somewhere near the stoichiometric ratio in each case. Not exactly at it, but near it, depending on how you do the calculation. So going back here, we're interested to estimate the temperature of a flame. We have to know the enthalpy of the reaction, the stoichiometric ratio. We also have to know how many inerts we have left over. There's a certain amount of heat given by this reaction. And if that heat only has to heat up the products of the reaction, I'm going to get the highest temperature. So if all I've got is fuel and oxygen, that's great. But if I'm burning in air, for every mole of oxygen, I got about 4 moles of nitrogen. And that means that over here, the heat, which is a fixed value, is not only has to heat up the carbon monoxide and dioxide, and the water vapor, but it also has to heat the inert nitrogen that's just coming along for the ride. And that's why it turns out that an oxyacetylene flame or an oxypropane flame have significantly higher heat intensities than a flame burning in air, because a flame burning in air has all this leftover nitrogen. And so I only get a heat intensity of a low value, something on the order of 100 watts per square centimeter, if I use an air burning flame. Now, what I have here to kind of illustrate some of this, this is going to be an air burning flame. In fact, if you look carefully at these torches, you'll see there's little holes down here in the torch. And what happens is the fuel comes up. Actually, the fuel comes up through here. There's a little hole, I'll pass one of these things around later, a small little hole that creates a jet of gas coming right through there. And a jet of gas flowing at a high speed like this actually creates a suction, a vacuum by Bernoulli, right? It's called a venturi. And that sucks in the air through these big holes. And in here, I pre-mix everything. So this is what's called a pre-mixed flame. We'll go over those in a second. And then it comes out the end and burns out in the air. So this is a pre-mixed flame. And this is propane. This is C3H8. This is what's called MAP gas, which is actually a registered trademark. And MAP gas, somewhere here, if this thing shows up. Okay, this MAP gas is C3H4 versus acetylene. Turns out MAP stands for methyl acetylene, and methyl acetylene has this formula. Acetylene, well, let's go over here to acetylene. Acetylene is a triply bonded carbon with two hydrogens on the end, C2H2. Methyl acetylene is a triply bonded carbon with a methyl group on one end and a hydrogen on the other end. So you can see why this, hopefully you can see why, here's your methyl group, and that's methyl acetylene. There's your triple bonded carbon, and here's a single bonded carbon. Now the P stands for propadiene, and propadiene is two carbon double bonds. So here's my three carbons, but instead of having a triple and a single bond between the carbons and the hydrogens arranged in a methyl group and a hydrogen, propadiene has the same chemical formula, but it has two hydrogen symmetric with two hydrogens on each side and two double bonded carbons in a chain of three. But in both cases, I have the formula C3H4. So methylacetylene propadiene is actually a registered trademark called MAP gas, and we'll talk later about why it's a desirable type of gas. But because it has, going back to this plot, it has a higher carbon to hydrogen ratio, it has a higher burning temperature by almost a couple hundred degrees over propane. So we'll now do the demonstration. First of all, which one should have a higher burning velocity? Oops, gotta turn it on. Trick. Which one sounds like it's burning faster? The yellow one, right? This one's a little bit softer, more muted. And it turns out this has a higher burning velocity because it burns at a higher temperature, so more PDV, more velocity. It should also have a higher temperature, and you can't really tell, well actually you might be able to tell, this one burns a little brighter down here in this area than that one over there. But the easiest way to tell is to put a piece of metal in each one and see which one heats up brightest and fastest. And the methylacetylene is already glowing red, and the propane's just starting to turn red. You also saw the yellow flame coming off. Anybody know what that is? Pardon me? Sodium? No, it's not sodium. Sodium does burn yellow. Anybody know what turns it yellow when I get the thing in there? I'm not generating sodium. And it doesn't show up at the very beginning, it kind of shows up a little bit later. What happens is it's actually unburned hydrocarbons, and I'm actually generating carbon soot. Very, very fine carbon soot. These are buckyballs. I just made buckyballs. You're all breathing buckyballs now. Okay? Don't worry, carbon's fairly inert. We breathe it all the time. Basically, the carbon soot starts to glow because it's a solid and it's glowing red. And so most of the flames that you see that are yellow, when you see flames burning yellow, it's because there's soot in the flame. Okay? Now this is soot. It's too small for you to see, but it's basically because it's only partial combustion. Good clean combustion will burn clear. And if you want, You have to, if I go sweeping my finger through the MAP gas, I'll do it a lot quicker than I will through the propane, okay? I don't recommend, well, you can do it, whatever you want, but you can actually feel the difference, okay? So I'll pass these around and you can look at the different things. Also, we've talked about bimetallic strips several times and thermal stresses. This is a little high school physics or chemistry thing. This is just basically a bimetallic strip. If I heat it up, it bends. If I cool it off, it should straighten back out. So that's basically how a thermostat works. I've got to cool it off a little quicker. So if I cool it off now, I can heat it from either side, and it should still bend in the same direction because it's based on the material properties, not the side that I'm heating. Okay, it's not that one side's good. Certainly, if I heated one side faster than the other, if something would bend, even if it was not monolithic material, if I had a temperature gradient. But this is thin enough. There's not a temperature gradient, any substantial temperature gradient. This is because it's a bimetallic strip, and it always curves in the same direction. If it was a solid monolithic strip and I had different temperatures, it would bend away from the heat source in each case, and the residual strain, this thing actually has some residual strain right now because it's still warm, but once it cools down, it still has a little bit of residual bend because over time I bent it too far and it took some plastic set, but it always bends in the same direction because it's based on material properties. So I'm not going to pass around the metal piece, but if you want to, in fact, I'll just pass one around. You can look at the torch. You don't need to play with the MAP gas. Turns out MAP gas is not as intense as acetylene, but it's much more intense than propane. And so if you want more heating value, you use MAP. And plumbers do use MAP gas to improve their productivity. Now, before I get to that, there are other gases that actually have a higher heat intensity than acetylene. For example, one is C2N2. Does anybody know what C2N2 is? It has a name. What's CN? We have a chemist here, right? Cyanide. CN is cyanide. Why does cyanide have the taste of bitter almonds? Because almonds contain cyanides. Okay? When you eat your cyanides. In fact, I was on the plane coming back from Chicago yesterday, and they give us little nuts in the first class, and it has they give you a mixture of mixed nuts, cashews and almonds and pecans and stuff. I usually eat the almonds out first because I want to get my cyanide early. Right? But in any case, this is called Cyanogen. And it actually has a higher adiabatic flame temperature, maximum temperature, burning impure oxygen, than acetylene by about 100 or 150 degrees. There are other things. There's something called hydrazine, which is H2N2. Hydrazine is not as hot as acetylene. Hydrazine is typically used as a reducing gas. They put it as a blanket over nuclear reactors. When they shut down the steam boilers in a nuclear reactor, they put this over the water to keep the oxygen out of the water, because the oxygen that gets in the water when you cool down the nuclear reactor will cause corrosion of the reactor. So they basically put a blanket of hydrazine, or bubble it even through the water, to keep the free oxygen down in the water so that you don't get corrosion when the reactor's not working. But cyanogen, one year I had a student who got interested in cyanogen, and so he went and got all kinds of information on it. It's called cyanogen, or oxalodinitrile. He says, probably if you're trying to convince someone to weld with it, you could call it oxalodinitrile. Otherwise, it's cyanogen. The dictionary says it's a rocket propellant, a fumigant, a military poison gas, and a welding gas. So, if you want to weld with a poison gas, you can. Now, it turns out that back in the early days, before we really had arc welding, people used to do all kinds of things to get higher heat intensities than they could get with just burning acetylene. And in fact, acetylene has not been around for a long time. The story with acetylene is basically that there was a guy in North Carolina near about the same time as the Wright brothers, actually maybe a couple of years earlier. And he can't remember because someone borrowed my book and didn't give it back, but there's a book called Jefferson's Welding Encyclopedia that tells the story of how acetylene was developed. And this guy can't remember what he was trying to synthesize, but he had a little arc furnace, and he would put calcium, limestone, basically, and carbon in a arc furnace. Let me see if I can remember what all this is. He started out with limestone with calcium carbonate plus carbon, and he would form calcium carbide. This is arc energy plus calcium oxide, I guess, right? However all that works out. No, he was driving off the CO2 plus CO2, I guess, okay? So he's driving off the CO2 and the arc energy had excess carbon, and he would form this calcium carbide. And calcium carbide, well, he didn't know what he's forming. He was just trying these experiments. And whatever he's trying to do, he didn't think this was any good. And so in typical environmentally friendly manner of 100 years ago, he went to dump it in the river outside behind his little shop. And as he dumped it in the river, something caught it on fire. Because it turns out that if you take calcium carbide, the way we make acetylene is you take calcium carbide and you mix it with water, and it makes C2H2. Plus, there's the calcium hydroxide. And it's balanced, even, isn't it? Or no? I gotta have a 2 there, right? So what I have to do something here? H2O. Do I need I need another 2. Okay, now it's balanced, I think. So all you have to do is you take calcium carbide and mix it with water, and you automatically produce this triple bonded acetylene. And you make the calcium carbide in an arc furnace. And the guy who did this in North Carolina, he thought it was kind of curious that when he poured this in the river caught on fire. Of course, it wasn't a big fire, but he saw flames coming up off the water. And he thought, that might be useful. And so he ended up starting a company out of this, which later became part of the Linde division of Union Carbide. And they basically made oxyacetylene cylinders. And I'll bring in a B cylinder probably tomorrow. But the B cylinder for acetylene is about this high. And the reason it's called a B cylinder is because it originally was the headlamps on buses. This was when you had horse-drawn buses. And then in the early days when they actually had motor carriages, the first buses, actually there was laws because they were afraid these things going so fast with, they were going 10 miles an hour down the streets. They were afraid they were going to kill somebody at these tremendous velocities down the streets. And they required them to have lamps. But they didn't have electric lamps and batteries and things back in 1900, so they actually had little acetylene lamps. And these little B cylinders were the bus lamps. They were the headlamps for the carriages back around 100 years ago. And that started a business, and people were doing welding and trying to find other gases. So I've never heard of anyone using cyanogen as a welding gas, but the dictionary says they did. And probably 100 years ago, when people weren't as concerned with worker safety, they probably did use it. So if we go back again to our flames, we can get different intensities with different enthalpies, different oxygen fuel ratios. It turns out if I go back to this one, so inerts are important, stoichiometry and enthalpy. These are the 3 key things that determine the temperature. The combustion velocity, it turns out that a pure oxygen flame with more PDV work will give you about 10 times the velocity of an air flame. And you'll get about 3,000 degrees centigrade by burning a hydrocarbon air, roughly, plus or minus a couple hundred degrees, right, centigrade. If you burn that same flare, that same hydrocarbon in the air, you're only going to get about 2,000, well, actually no, you get less than that. You get about 2/3 of that on an absolute scale, and that's about 1,000 degrees. It's about 2,000 degrees Fahrenheit. Instead of 3,000 centigrade, you only get about 2,000 Fahrenheit. And if you go, remember I handed out this paper on the World Trade Center that I wrote? And basically I was just going back to this type of stuff. There's no way a flame burning in air can get to the temperatures of 1,500 degrees centigrade sufficient to melt steel. It turns out that burning in air, if you start with room temperature air and you start with a hydrocarbon, there's enough inerts left over from all of this. Where do I have my inerts equation? Oh, here. With the nitrogen left over, that there's, if this is 3/2 moles of oxygen from the air, there's going to be 6 moles of nitrogen. 4-to-1 ratio, right? So 6 moles of nitrogen over here, I end up with 2 moles, 1 mole, and 6 moles. I end up with 9 moles. And if it's the same amount of heat, I'm only going to get about 1/3 the temperature rise that I get if I have no nitrogen around, because I'm heating up 3 times as much gas. 9 moles as opposed to 3 moles. And if I'm getting, let's say, 3,300 Kelvin as an adiabatic flame temperature for pure for acetylene burning in pure oxygen, I'm only going to get 1,100 Kelvin or so if I have all this nitrogen around. And 1,100 Kelvin is going to be 1,700 degrees Fahrenheit. And so it's very hard to even get to 2,000 degrees unless I do something to preheat my incoming air. And in fact, that's what Sir Henry Bessemer, whether he knew he was doing it or not, when he developed the Bessemer converter, which basically is a vessel to melt steel that has a shape sort of like this. It has a snout on the end, and here's your steel down here in the bottom. It's a great big vessel, and you blow your air in onto the steel surface, but to get out, the air has to go back that way. So guess what I'm doing? I'm preheating my air coming in to my cast iron to burn the carbon off my cast iron to turn it into steel. I'm preheating it with the exit gases. Now, it wasn't a very efficient way to do it, but he was the first person to learn how to get temperatures by burning in air that were sufficient to melt steel. Because ordinarily, you can't get to 1,800 Kelvin unless you're going to preheat your air. And so then after that, who came along? Well, actually, I don't know who invented it. After Bessemer's converter, which made Andrew Carnegie the richest man in the world, the Bill Gates of his day, someone developed what's called the basic open hearth furnace. And the basic open hearth was just a much bigger version, where instead of blowing it in this way, you actually had huge banks that were, and these things were the size of a football field, of just brickwork, and you had 2 of them on either side. And so you would have your hot gases come into the steel vessel. It's not the same steel vessel, and you have them exit on this side. And what you would do in the open hearth is for about 8 hours, you would flow the air in this way to refine the steel, and it would go past this football stadium-sized brickwork lattice, which had all been hot because before you used to flow it back through the other way. And so you're preheating with your exit gases all the brickwork, and then when you reverse the flow, you got hot brickwork which preheats the gas coming in. And so you would reverse about 2 or 3 times a day. You would reverse the flow of gas through these football field size brickwork lattices, and you had huge thermal masses that were basically storing the exhaust gas heat. And that was the basic open hearth, which was the way of making steel until, what, the mid-60s. So from 1900 to the mid-60s, you had huge basic open hearths. And in their great wisdom, it turns out to make steel that way, you might melt the steel for 36 hours. U.S. Steel, in their great wisdom, in I think like 1972, built the world's last open hearth furnace. And it was like a 500-ton furnace. It was huge. It was bigger than anything else anyone had ever built. It was also a dinosaur at the time it was built. Because what had happened is, in the late 50s, in Austria, some people determined that blowing pure oxygen in something similar to the Bessemer process, with pure oxygen, you didn't have to preheat your air. In fact, the pure oxygen they blow in there actually goes in many times as liquid oxygen, because it's going to get hot and expand and everything else. And that's called a basic oxygen converter. And it takes 20 minutes to refine your steel in a BOF. Or actually, well, it may be 40 minutes with loading up and shutting down and everything. But it's only about 20 minutes of actual oxygen blow time. So you got your production time in a 300-ton vessel down from 36 hours to 20 minutes to 40 minutes. And U.S. Steel in 1972 wasn't intelligent enough. They went out and spent what would be the equivalent probably today of $500 million building this dinosaur, because that's what they had built for years. Even though the technology was out there and other people had built 200 and 300-ton converters that could convert steel back in those days in 1 hour, they built a huge one, twice as big, that could do it in 36 hours, and they couldn't figure out the economics of it. But that's what they were getting paid the big bucks for. If you want to know what my opinion is of the U.S. steel industry's management in the 1970s, I'll tell you someday, having worked for them. Not U.S. Steel, but their competitor. Anyway, pure oxygen gives 10 times the velocity of an airflame, and the velocity is proportional to PDV work. So if I want to get high-intensity heat sources with flames, I've got to use oxyacetylene flames and run everything as hot as possible because of this T-squared dependency. Now, how come I only get 2 to 10% efficiency, even if I get these hot 3,000 degrees 3,000 degrees centigrade flames? Well, it turns out if I have this flame that's shooting out, it turns out I get a gas boundary layer against the surface. So I've got a surface of some solid or some liquid here. The gas shoots out, and you end up forming a lower velocity. You have friction against the surface of the condensed phase, and the gas has a lower velocity in the boundary layer than up here. How many people have not studied boundary layers in some other engineering course? So everybody knows what a boundary layer is? Boundary layers are the way that you can fly. You know, birds fly. The Wright brothers figured it out. So it turns out there is a thermal boundary layer. When you have this velocity boundary layer, there's a thermal boundary layer here, and the heat has to diffuse across this stagnant layer of gas. And that's what changes your efficiency from 100% heat transfer efficiency to only 2 to 10% efficient. Flames are only 2 to 10% efficient. Most of the heat goes off to heat up the surroundings in the air, not heating up the workpiece. You're basically heating up the welder, the person doing the welding, as opposed to heating up the workpiece that you want to heat up. So the gas boundary layer, which we will get back to when we talk about cutting technology, the gas boundary layer is the major problem. I think I'll save, since we're at time, save the other stuff for tomorrow. Okay, see you tomorrow. And next week we'll meet every day. I think you have 2 more lectures on the 3371 part of the course. And you'll get those